Okay, so good morning class. Our lesson for today is about traverse. So we can define the traverse as a series of connected lines whose lengths and directions are to be measured, and the process of surveying to find such measurement is known as traversing. No, so for today we're going to learn several techniques in order to compute the area inside the traverse. So simple method that is useful for rough area estimates would be the graphical method. So under this, so this traverse is simply plotted to scale on a graphing paper, and the number of squares inside the traverse are counted. So we can also use yung basic formulas. Okay. So for example, for this case, in order to find the area of a traverse ABCD, okay, so we can break down this figure into two triangles, no? So the area of ABD plus the area of BCD. So recall the area of a triangle for given two sides and one included angle. So we can use the formula 1/2 AC sine of the included angle. So for this case, we can apply the same formula. Okay. So the area of this given traverse is equivalent to the area of this first triangle, second triangle, and the third triangle. Now, if we're going to use the same formula, okay, for the triangle, 1/2 the two sides and the included angle. So we need to, of course, okay, determine the length of this side and also this side. And of course, assuming that this is given, so we can use the Heron's formula to find the area of the second triangle. So by adding the area of the three triangles, this will give us the total area for this given traverse A, B, C, D, E, A, no? So for the balancing of angles, so before the areas of a piece of land can be computed, so it's necessary to have a closed traverse, no? So the interior angles of a closed traverse, okay, should be equivalent to this formula, n minus 2 times 180, where n here represent the number of sides of a traverse. So this represent yung magnitude ng error of closure, which might be due to the angle containing mistakes for this angle C, no? So the closure of a traverse is checked by computing the latitudes and departure of each of its side. Okay. So for this case, we're given here the line segment AB. So the departure is along the east-west direction, while the latitude is along the north-south direction. Similarly, if we're given a traverse or line segment CD, so this component represent the departure, and this line represent the latitude, no, for the line segment CD. So the latitude of the line is its projection on the north-south meridian, while the departure of a line is the projection on the east-west line, no? So the northeasterly bearing has, of course, the latitude and departure. So for the error of closure, consider the following statement. If start at one corner of a closed traverse and walk its line until you return to your starting point, so you have to walk as far north as you have walked south and as far east as you have walked west. Therefore, the summation of the latitude should be equivalent to 0, and also the summation of the departure should be equivalent to 0. Error of closure. So when the latitudes are added together, so the resulting error is considered as the error in latitude, or E sub L, no? And the error resulting for the adding departure together is called the error in the departure, or this is E sub D, no? So if the measured bearings and distances are plotted on a sheet of paper, so the figure will not close because of the presence of E sub L and E sub D. So to determine the magnitude of the error of closure, so we can use this formula, the square root of E sub L squared plus E sub D squared. So error of closure represent this line segment from this point up to this point. So obviously this is a right triangle, so we can use the Pythagorean formula, no? Now to compute the precisions, we have the formula. So this equivalent to the value of the area of closure over the perimeter. So typically, yung precision values for the rural land is 1 over 5,000. So take note that the precision should be expressed to unity. Okay, so the value of the numerator should be 1 over a certain value. Then for suburban land, the precision value typically is 1 over 7.5. And for urban land, 1 over 10,000. So for example, we're given here a traverse, okay, from, say, assuming that the starting point would be point A to point B, C, D, E, then going back to the point A, no? So for the first line, which is the line segment AB, we're given here the direction, south 6 degrees, 15 minutes to the west, as well as the length, no? So 189.53 feet. So similarly for the rest, B to E, we're given here the direction as well as the length. Now, if we try to consider the first line segment, AB, so to compute the departure value, so this is along the east-west direction. So this is going this way, so to the left, okay, or to the west direction. So this by sign convention, the sign should be negative now. So sine of the given angle is equivalent to the component or the departure value of the line segment AB over the given length. Okay, so that's why if you want to obtain the departure value of the line segment AB, it's equivalent to the given length, 189.3, then sine of the given angle here. So this will give us negative 20.63. Now for the latitude value, so we're after to this component, okay? So we have to use the cosine function, okay? So cosine of the angle is equivalent to this component, the latitude of the line segment AB, over the length, no? So to obtain the latitude, this is the length times the cosine of the angle. So take note that the latitude or the latitude value for the line segment AB is going uh, downward. So by sign convention, the sign is negative. So that's why we have here negative 188.40 feet. Next, if we try to consider the second line segment, BC. So the departure value for this case is going to the right. So this is positive. So to obtain this component, this is the given length times sine of the given angle. Or for this case, yung bearing, no? So it's equivalent to 86 positive 0.62. So for the latitude value, so this component, so we can use the cosine function. So cosine of the angle is equivalent to the latitude, okay, for the line segment BC over the length. So to obtain the latitude is equivalent to the given length times the cosine of the angle. So again, for this case, the latitude component is going downward, okay? So the sign here is negative. Okay, so negative 152.27. So we can tabulate our values. So the given side, the bearing, and the length. So latitude and departure values. So by doing the same process for the remaining sides, we can obtain the following values now for the latitude and departure. So we can sum, okay, the length here, starting from the side AB and to the last side, which is EA. So this value represent, of course, the perimeter. Now, if we try to sum all the latitude values, okay, this will give us E sub L, so the error in latitude. Similarly, for the departure, if we try to sum this will give us this value, negative 0.163, no? So this represents the error in departure. Now to quantify, okay, or to compute for the error of closure, so we use this formula. So it's equivalent to, so just substitute this 2. This give us 0.182 feet. No? Now for to compute for the precision, so this is the formula. So error of closure is 0.182 divided by this perimeter value. Okay. So now to express this precision as unity over the certain value, so we need to divide both numerator and denominator by 0.182. No. So the answer here is 1 over, so the answer should be 5,161.87. So to round it up to the nearest whole number, so the answer should be 1 over, so 1 over 5,162, no? Okay, so this is the final answer. So this is not correct. Okay. So that's the end of our presentation or lecture for today. Okay. So we're going to consider this next example, next meeting. So thank you for listening.